Hello. In this video, we are going to study series and parallel connections of resistors. So consider the following circuit, which has two resistors in series. So they're connected back to back, and this is what we call being connected in series. Let's analyze this circuit. Let me just define all the voltages and currents through the following elements, and I use pass-through sign convention here. When we analyze this, let's just use KCL, KVL. So first, let me write the KCL equations. The first equation is for this node here, the second one is for this node, and the third one is for the bottom node. Right? These are just the KCL equations. Current in minus current out is equal to 0. And I can simplify these, and all these currents are the same, and just call that current I. Next, I can do KVL. There's only one loop, so I just do KVL around this loop. All the voltages up minus all the voltages down is equal to 0. I can rewrite this equation, and so I have now one equation resulting from KVL. So if I just summarize this, this is what I get from KVL and KCL. And then finally, I can write the equations for each one of the components, each one of the resistors. I write Ohm's law, so that relates I1 and I2 to V1 and V2. And now let's combine these. So I take the KVL equation here and then replace the values of V1 and V2 by what I get from Ohm's law. I know that the currents are the same, right? And I can simplify. Basically what I see is that I get an expression for this current I. Now when I look at this, this looks very similar to this circuit, right? If I just have one resistor R, I basically get a very similar equation. And really, two resistors in series behave as one equivalent resistance, where the equivalent resistance is just the sum of these two. So when I want to analyze the circuit at the top, I could actually just combine these two resistors, R1 and R2, in this R equivalent, and just do the analysis on this bottom circuit instead, to make my life easier. So that's the idea of combining two resistors in series. What I can also do is actually look at what is this voltage VO over this resistor R2. I calculated this current I before, right? And VO is just I times R2, and I can work out the equation. And what I see is that VO divided by this VS is given by this equation here. And this is what I call a voltage divider. The voltage, the total voltage, Vs, that's over these two resistors, R1 and R2, only a portion of it is visible over R2. And that's the result of this voltage divider. Next, let's look at two resistors in parallel. So basically, in parallel means that they are connected this way, where both ends are connected together. And again, we can specify the currents and the voltages for these elements, and we can write KCL. So for the node at the bottom and the node at the top. And actually these two equations are just linearly dependent, and I can again simplify it a little by defining this current I, which is split between I1 and I2, right? So I1 plus I2 is equal to I. I can now also do KVL. So I can do KVL in the first loop, then KVL in the second loop, and just rewrite these equations a bit. And so now, if I add in KCL again and Ohm's law, I have a new set of equations, and from this I can try to solve the circuit. So I take this equation here, plug in the current from Ohm's law. That's what I do here. Then I know that V1 and V2 are equal to Vs. I rearrange and I get this expression. And again, when I look at this, this looks very similar to a circuit like this. But now, this R corresponds to this equation, right? So again, my circuit with two resistors in parallel behaves as if these resistors are just one equivalent resistor given by this equation here. So I could simplify the circuit at the top to be the circuit at the bottom, and then just continue my analysis. I can also rewrite this equation here for my R equivalent as a function of impedances, which makes it a little easier. So the equivalent impedance is just the impedance for 1 plus the 1 for R2. Let me also now look at what is this current I2 that is flowing through R2. That's given by this equation here. It's Vs divided by R2. And I can solve Vs from this equation here and rearrange. And I basically see now that I2 is again a fraction of I that's given by this expression here. And this is called a current divider. So this expression looks actually very similar to what I had for a voltage divider. However, note that the resistor here at the top is the one in the other branch. It's R1. It's not R2, it is R1. So for the current divider, it is the resistor in the other branch divided by the sum of the two resistors. So, resistors in series and resistors in parallel. I kind of glossed over a little bit about what it means for them to be in series and in parallel. They actually have to be connected exactly this way. For resistors in series, one end of one of them has to be connected to one end of the other with nothing else connected to it. So if there is something else connected, this is no longer in series, so this cannot happen. For parallel, both ends have to be connected, and there can be nothing else in between. So if I have another resistor here, now these resistors are not in parallel, so this is also not in parallel. So it's really good to be able to identify exactly when the resistors are in series and when they are in parallel, because otherwise you cannot apply these equations. And these are the equations that we saw, right? So we can replace resistors in series by an equivalent resistors, or the ones in parallel by an equivalent resistance. And we had the equations for a voltage divider and a current divider. And I can extend this to more than one resistor in series or in parallel. 3, 4, 5, no matter how many you want, and then it kind of looks like this. Okay, so resistors in series and parallel are actually very powerful techniques to simplify circuits and simplify your analysis.